Okay, then now for something completely different. So we are now entering the second phase of our winter term GLM FMI discussion, and so far we've discussed any kind of designs for brain mapping, and now we want to discuss psychophysiological interaction designs. And usually referred to as PPIs in the brain imaging community. So in your papers that you discussed in all these other courses, did anyone come across PPI? No. Was there no PPI paper? Never came up? Were there GLM papers where regions lit up? Yes. In FMI. Were there DCM papers? Were there multivariate pattern classification papers? So you only had GL. I try to understand what this person said on your phone. So there were only GLM and MVPA papers for FMI. Do I get that correct? Yeah. Okay. Who chose these papers? Anyway, good. But it's fine. So from the GLM perspective and also the MVPA perspective, what one can do with fMRI, as we discussed, obviously, is localization of cognitive processes. Yeah, I mean, we discussed that in the fMRI part in the Hütte book, and we now discuss GLM a lot here. So the aim is of GLM and also MVPA areas is to map processes or representations of external event to brain areas. Yeah? So whenever you do a GLM analysis, like the ones that we discussed so far, and if you do an MVPA analysis, you say there, in this region, there it is. You can't say anything more. Yeah? Anything more is wild speculation on the side of the authors. That's the outcome of a GLM FMI study. So that's GLM and MVPA typical analysis. Any comments on that? Any disagreements with what I just said? No, good. Now, psychophysiological interactions and also DCM analysis that we will discuss in the summer term are trying to say something about how brain regions interact in a cognitive process depending manner. Yeah, so interactions of brain regions in cognition-dependent manner. And these kind of things are usually referred to as connectivity. And then you have these debates about effective versus functional connectivity. Anyone ever heard effective versus functional connectivity? No. So in all your other courses, the brain consists of a lot of modules that don't interact, and that's the brain. Good.
I think we just didn't like do any analysis, but you can like no. I mean, in no paper there was functional connectivity analysis, but I think, for example, Adrian still didn't present that brain as independent modules.
Well, I mean, this is actually a little bit of a problem in the sense that, especially if you do GLM analysis and then the authors write something like, yeah, this is now the network, and these network interactions generate the complex cognitive processes that we are interested in. Well, that's not what the data analysis actually shows. So, in a sense, one should. This is also a little bit annoying in GLM papers usually, or MVPA papers that try to make too much of a point from what they actually analyze. In any case, there are analysis methods to look at also how brain regions interact. And the typical analysis techniques in at least cognitive neuroimaging, so when it's about cognitive processes and not about resting state only, are PPIs and DCMs. In the whole resting state literature, you also find a lot of correlation stuff, but this always is independent of any external perturbation, so independent of any experimental influence, because it's resting state, so people didn't do anything in the scanner, just did mind wandering. The problem, that's the good news. So we're now talking about connectivity and interactions of brain areas, not only localizing processes. That's the good news. The bad news is these methods, so PPI and DCM, also don't tell you how neural populations solve certain tasks. So it's on the surface, and if you listen to the rhetoric of people talking about effective functional connectivity, you would have the feeling that they actually explain, based on the interactions of brain areas, how the brain can do cognition. That's not the case. But to appreciate this, of course, that this is not the case, one needs to know what actually is happening, so that one also can read papers that argue in that way, with a critical mindset, or critically evaluate these. So you never so nobody has heard the term PPI before. Just to make sure that I know where to start, and that I don't always say, as you know. Okay, so then it's completely new, and you never heard that. And this is what we will then now start. As I said, in the summer term there will be DCM. PPI, and this is why we're doing that right now, is a DC. It's not a DCM analysis; it's a GLM analysis. So PPI, a form of GLM analysis. And it's actually a fairly specific form of GLM analysis. Maybe it's an uncover analysis, so an analysis of covariance with interaction. And because this is the case, and because it's implemented in a GLM manner, it pays to appreciate PPI from the perspective of the GLM, meaning from the perspective of ANCOVA. And if you're dealing with ANCOVA, you already deal with a mixture of factorial and also discrete and continuous, so regression-like designs. So it pays to understand PPI, to understand ANCOVA, if you want to understand how PPI is actually done. And to understand ANCOVA, specifically with interaction, it pays to understand ANOVA. With interaction. So what we then will do in the next hours is to basically work our way from ANOVA via ANCOVA to PPI. So we will go this way because the main reason is when I studied and tried to understand what PPI is, could never understand what it is until I understood ANOVA and ANCOVA. And then it was clear. That's just the way to go. If you read the original PPI paper by Carl Friston from 1997, so this is also quite old, not quite old, but relatively old. It's really difficult to understand this paper, essentially because it doesn't really make the connection to ANCOVA that explicit, and it's a little bit mysterious, this paper, like many Carl's paper. But if one goes this way via ANOVA, ANCOVA, then it's actually straightforward and it's relatively easy to understand what PPI is, and also enables one to critically appraise in what sense this now relates to connectivity of brain areas. PPI is commonly used. So it sometimes certain things disappear and nobody's using them anymore. Like for example, adaptation paradigms, and then we go to a conference this year or last year, and then suddenly adaptation paradigms are back again. Same with PPI. Sometimes disappears and then it reappears. It's weird. Anyway, PPI happens, and hence we will discuss it in this order that I just explained. Any questions? Any alternative suggestions? No. Okay. Then now let's take a step back. Forget about the whole brain imaging business and these strange papers that you read in cognitive neuroscience, where it's not really clear what people did and whether they understood what they did. But let's go to basic statistics, where it's relatively clear what's going on. And let's talk about ANOVA first, because to understand ANCOVA, we have to first talk about ANOVA. Actually, if I say ANCOVA, who knows what ANCOVA is and could give a definition?
Analysis of covariance.
Yeah, and what's the specific thing of ANCOVA with respect to ANOVA? So what's the main difference?
It's covariance between two variables and not the variance of one variable.
Yeah, that's what one would think, but that's actually not the case. So ANCOVA designs are mixtures between the categorical ANOVA designs and multiple regression designs. They are called ANCOVA designs. We will get to that. Let's start with ANOVA first, and specifically ANOVA designs with interaction. And the reason why we, of course, talk about ANOVA designs with interaction, because in the end, the psychophysiological interaction will be an interaction. Yeah? So the interaction is important, and so we have to first, if we want to understand what PPI is, remind ourselves what interactions mean in statistical terms. And interactions come about in ANOVA designs, and specifically in multifactorial ANOVA designs. To get to multifactorial designs, we first should start with something even simpler, namely one-way ANOVA designs. So the first thing to discuss, maybe to make a list of what we need to discuss until we can understand PPI is first we talk about one-way ANOVA. Then we talk about two-way ANOVA. And then essentially about two-way or multifactorial or whatever ANCOVA. So that's the stepwise approach to get towards PPI, because this is essentially the same. Yeah? So we're taking a bit of a detour, but this detour pays off, believe me. Trust that this is not a joke. On this detour we also learn again about fairly fundamental statistical analysis techniques that of course you know anyway, because you all study psychology, and of course everyone who studies psychology is very proficient in statistics, because that's what you study in psychology a lot, but it makes also sense to revise these things. So one-way ANOVA, that's our first topic. From a psychology statistics perspective, when do you use one-way ANOVA? As opposed, let's say, to simple linear regression or t-test.
The factor is a categorical variable, which is more than two, which is not binary.
Yeah, exactly. So in this sense, one-way ANOVA is the extension of two-sample t-test. So where you have categorical independent variables, extension of two-sample t-test to more than two groups. Yeah? So essentially, you would love to do a two-sample t-test to compare the outcomes of two groups, but it turns out that a two-sample t-test only works for two samples. So you need to do something, and for some reason somebody says, yeah, you cannot do pairwise comparisons. There's a get multiple comparisons problem. And then you say, okay, I can do ANOVA. And then this other person says, yes. But if you find something is significant, you only know that there's a significant difference, but you don't know where it is. And then you do then you do binary comparisons, but you're only allowed to do these binary comparisons if you first found a significant effect. This is all, I don't know, this is what people get taught, and also what I taught. It's, you can do whatever you want. Yeah? So don't believe in these kind of, I mean, definitely you cannot do a two-sample t-test if you have three groups, because this doesn't work in terms of what you compute. But all these things, you're first allowed to do this, and then this, and not this, and only if this, and then you have to do Kolmogorov-Smirnov. You can do whatever you want as long as you know what you are doing and you can justify what you are doing. Yeah? If you don't know what you're doing and you're just clicking things around in SPSS or R, and you don't know what you're doing, then you might want to follow some rules, but even then, why? I mean, maybe you want to follow some rules. Anyway, let's talk about one-way ANOVA then from a more modeling perspective, basically look into the one-way ANOVA model to get started with the whole thing. This is now stuff that in the PMFN book you find in this fundamental design part that is also online under the GLM stuff. We are starting not from the very beginning in this section, but we start from where I start with one-way ANOVA, because we don't really need the simple linear regression business for PPI. So we now want to talk about one-way ANOVA. and first introduce the underlying model, and then discuss its GLM implementation, and then we're essentially done and can go to two-way ANOVA. So in a one-way ANOVA setting, we said that we have multiple groups, yeah? And in these multiple groups we have, of course, multiple data points. Yeah? So remember that you somehow use ANOVA if you have more than two groups, but in these groups you have also multiple data points. Yeah, let's assume for the case of the example we have three groups, and we denote the data that we get by Yij, where I denotes group, and J element in group. Yeah. So to make this concrete, if we have, let's say, three groups, and in each group we have, I don't know, 4 data points, so that I don't have to write this much. We have in the first group y12, y13, y14. That's group 1. Then we have group 2. Then we have y21, y22. We assume a balanced design, so we assume that we have the same number of data points in each group. That's not completely critical, but if one then wants to show kind of goodness of estimators and so on, in general, it always makes, if you want to estimate the effects of your group treatments in a good way, of course, and in a way that is the same across groups, assuming that they have the same variance, then of course it makes sense to have the same number of data points for all of them. Also makes things a little bit easier in terms of writing. Yeah, so this is now some hypothetical data set. So whatever you want to think what this is. So one thing that is important, this is not a repeated measures design because we want to use the spherical covariance matrix. So you should think that these are readings from, let's say, individual rats that were exposed to certain medications, or participants that were treated with different forms of cognitive behavioral therapy, or let's say this was cognitive behavioral therapy for depression, this was psychoanalysis for depression, and this was nothing, or whatever, yeah? So think of your favorite study question, but think of independent experimental units. So it's not the same participant measured across the different treatments, but what the treatments are, whatever you like. Yeah? Now, the ANOVA model that is used to describe these data points is, of course, a probabilistic model, and takes the following form. So this is now a probability density. So the probability density for the ijth data point, so assuming that there's a random variable from which this ij data point is a realization, has a normal distribution with a group-specific mean and a a common variance. Yeah, so that's fairly important. So that's group specific mean. Or expectation, I should say. And this variance is variance identical variance for all of them. So the thing is that the sigma square doesn't have any ij subscripts, so sigma square is the same value for all data points. Yeah, the expectation varies over groups, but the variance doesn't vary. So this is what this says is that the ij's data point has a normal distribution, the expectation of which depends on the group, namely on I. The variance is the same for all of them. So this is the first kind of assumption that one puts into a one-way ANOVA if one later on wants to do inference via T statistics. So that you can, of course, do ANOVA in a normal distribution free manner, but then you cannot use T statistics or more importantly F statistics. Of course, in ANOVA you usually do F statistics and F tests, but if you want to use the F distribution for inference, then you need to assume from the very beginning that you have this normal distribution. So if you haven't encountered the normal distribution that early in one-way ANOVA previously, but later on in your course encountered the F distribution, then something was a little bit, don't know, because you only get the F distribution if from the beginning you put in the normal distribution. Now, this, of course, is the same thing, and this is also very similar to what we've seen previously, of course, for the GLM. This is all GLM business, as saying that the ijth data point arises from a group-specific contribution mu I and a data and group-specific error that is independent of all other errors. Actually, this is the maybe an additional assumption that is more explicitly seen in this case, although it's actually also seen in this case, only that we're not talking about all the whole data yet, where the error contribution is again normally distributed and centered on 0 and variance sigma square. Yeah, so these are univariate normal distributions, and the fundamental model of the ANOVA is just that the data point is given by this group-specific offset plus an error, and the error is specific in the sense that the errors are independent. Yeah, that's the only thing. So the variance is still the same for all errors. So have you seen the ANOVA, one-way ANOVA model in this form? How did you see the ANOVA? So what did you do about ANOVA? Or did you just compute variances and then compute an F value? What did you do for ANOVA? You must have done something for ANOVA. You cannot just heard the term and...
just computed the F distribution, I think.
So the F test, sorry, the F statistics, because distribution, I guess you didn't compute, but the F.
With other formulas, but it was the same. Like there is a variance, so there's a group mean and variance, and then the deviation of every data point, and then we had a common variance for all groups, and then the deviation. So it was a double deviation test. Deviation from the group mean and deviation from the overall mean. Yeah, that's it. Or it was more graphical.
Yeah, I mean, this is what you also find in this in my fundamental design business. This is actually the classical variance partitioning view of ANOVA. This is also, so this then works with these sum of squares total, sum of squares between groups, within groups, and mean squares, where you divide the sum of squares by the degrees of freedom and so on. This is the same thing. If you're interested how this, what you then did there, relates to what we're doing now, this is also in the script. It's actually quite interesting, or relatively interesting. It's a little bit. It's not interesting at all, but it's one can relate this. This is the point. It's a different view on the whole thing. Okay, but then the good thing is also that you learned something new here and something that is simpler. But then I also know what is still being taught in undergrad statistics, namely this classical variance partitioning business. Good. So far, so good. Now we have to talk a little bit more about these group-specific means, because they are also modeled in a specific manner, and the basic way they are modeled, which we will then overwrite after we introduced it, is as follows. It's assumed that the group-specific expectation is given by a constant offset of all groups. So, for example, in terms of cognitive, these different therapy forms, this measures the happiness after treatment, and everybody is at least happy around 0. That's well, that would be a boring offset, but let's say everybody who's still alive is non-zero, whatever. There is a common offset to the data points. That's whatever you want to think about this. Like if it's the MR signals, so if these are MR signals from different participants, average of the whole brain, then the MR signals have a common offset of 180, and then each group treatment makes some contribution. So there is an offset, mu0, and there is an effect of each factor level or of each group treatment. Yeah, so that's the offset. That's Cardi B's ex-husband. You're not into pop culture that much as I am. Offset, Cardi B. No? He's one of these Migos rappers. Mumble rap? Anyway. Sorry. Alpha I, that's the group contribution. Or treatment contribution, however you want to call it. Now, if one now wants to express this thing that we have here, that the expectation of the ijth data point is given by mu I, which in turn is given by a common offset plus a contribution of the group or the treatment or whatever, or the level of this one factor. So these are all the same things. Then one can write this in design matrix form, and this is what we want to do next, so that we get to the GLM form of the whole thing. So if we want to put the whole thing into GLM form, then the first thing that we do is to organize the data into a long vector, because our GLM, of course, is still the same GLM as we introduced fairly early on. So that's our GLM equation, and we now want to implement or formulate this ANOVA model in GLM form. So our Y needs to be an n-dimensional vector. So we first write our data points one below the other. So, and we start with the first group. Now we can actually write them all out. It's not that many. So that's our data vector, y. I try to give it a nice bracket. Yeah, so that's y. We now have the n is what? What's n? It's the number of data points, but how many data points do we have? If we have 3 groups and 4 data points in each group. Alternatively, count the y's here. 12, yeah. So our n is 12. So we have a 12-dimensional vector. And that means, no, that doesn't mean much for the moment, but we have formulated our data vector. Of course, later on we will also apply ANOVA and COVA designs to the MR signal, and then the y is again the MR time series. Yeah. So for currently the y are our data points, but later on we will of course return to the idea that y is the observed MR signal. And now we want to create an expectation vector here, mu, so that the ijth data point has expectation mu I. So any suggestions about if we now have our y here, what I need to write for mu? So we would just want to write this in vector form. That's the only thing. Yeah. So
mu1, mu2, mu3.
And how many of these always? So if we want to align it with this?
It's done 4.
Yeah. So so I'm just trying to match here the expectation. So basically writing out. So another way you can look at it, what I'm doing right now is to just write out this yij equals mu y for I from to 1, 2, 3, and j then 1, 2, 3, 4. And of course the mu is only depending on I, and wants to model things like this. Oops, sorry. 3, 3. So this is just the matching expectation to each of these, then of course the model says that in addition to this constant contribution, not really nice. Something like this. There's of course the error contribution. So there is epsilon 1, 1, and now I'm not writing this out explicitly. So there's epsilon 1, 2, and so on to all of them, and then we have written out this thing for all of our observations. So that's our epsilon vector. And now we also said that the mu I is given by, so the group-specific expectation is given by an offset and a group-specific contribution. And this is now what we want to cast as design matrix and parameter vector, because remember that in the GLM, the expectation vector is always given by the design times the beta parameter vector. and we essentially just want to translate that. And this is what we now do, and I guess I do it here. So first of all, how many alpha I do we have? If I is given here, 3. So we have then in total 4 parameters. So our beta is mu0, alpha 1, alpha 2, alpha 3. That's our beta. And finally, we want to make sure that mu1 is mu0 plus alpha 1, mu2 is mu0 plus alpha 2, and mu3 is mu0 plus alpha 3. So we have to formulate our design matrix accordingly. So how many rows does our design matrix need? If we want to model our 12 data points. Exactly. How many columns does it have? So that we can multiply with our beta vector. Four, yeah. And now we just need to fill this design matrix in such a way that actually our mu1, our mu vector here, so these 4 mu1s, these 4 mu2s, and these 4 mu3s come out if we multiply them with the parameter vector. So what we see definitely is that we always have mu0 for all of our mu i's, yeah, so mu0 is always there. So we can first of all make this a little bit smaller now, write 12 ones below each other. Then we can multiply, so then we have one column and we multiply this with this beta vector, and we always have this mu0 contribution. Then for mu1 we want plus alpha 1. So we for the rows where we want mu1, we put in ones here, and for the other ones we don't want mu1. So if we model mu2, so this of course goes to these first 4 go to mu1, 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 mu1. These second 4 ones go to mu2, and these go to mu3. So here we have zeros, and then for mu2, what do I have to write? Yeah. And then? And for the last one? Exactly. So that's then our design matrix that instantiates or is equivalent, or however you want to, or implements, however you want to call it, this model here, yeah. So essentially, I don't know how you want to see it, but the ANOVA model consists of this group-specific expectation parameter, and that's the structural form, if you want, which is due to an offset and a group-specific treatment effect. So the alpha I is the group-specific contribution or effect. That's also what I should put here. And if one wants to implement that in terms of the GLM, so essentially what SPSS does under the hood is to translate this into a design matrix so that you can use the standard forms for the estimators, so the beta hat and the sigma square hat, to estimate it, and you don't always need to compute things with different formulas for different designs. Yeah? So we've now translated the ANOVA, one-way ANOVA model into GLM form. Why are we doing this? Because for PPI, we will look, and we have to look at the design matrix, because this is what you see in terms of PPI analysis when you use, for example, SPN. So we need to be familiar with the design matrix formulation, and we need to build on one-way ANOVA. So a one-way ANOVA, and also this formulation that we used here does not quite work yet because it's over-parameterized. So we have to adapt that. But all these things, in looking at the design matrix, will be important to understand why the PPI design matrix looks as the PPI design matrix looks. So let's stop here, and then next time start with what is called the reference cell reformulation of one-way ANOVA, and then play the same game with two-way ANOVA and ANCOVA. And once we've done that, then we can understand PPI. Yeah? Good. Then let's stop here if there are no questions right now.